In Chapter 2, we get introduced to alkanes. And by the end of the chapter, you should be able to recognize what an alkane is. You should be able to draw it in various types of drawings. You should be able to understand different rotations that alkanes can undergo, and which we call conformations, and understand that alkane is a particular functional group. Now, what do functional groups mean? So this is a new concept to you, and in essence, organic chemists really focus on functional groups, meaning groups that have a particular function. So different types of groups have different types of chemistry. And so we group them together, and we're going to see how this plays out. But the important thing is to recognize that the reactivity of a molecule depends on this functional group. So chemists need to know the various types of functional groups. Now, where can you get this information? If you're following along in Chapter 2, you actually won't find it in Chapter 2. And that's because in your textbook, they've placed it on the inside cover. So this shows most of the important functional groups. Now, there are many functional groups, but the ones that we're going to mainly be dealing with throughout the semester can be found in your inside cover. And the reason why it's placed in the inside cover is so that you can readily access that information. So the key is that you need to know them. Make sure you are reviewing them, once a day or so until you can easily recognize the various types of functional groups and how they play out. Now, I'm going to show you various structures of functional groups, and in order to do that, we demonstrate generic structures using R. And R simply denotes a generic carbon skeleton, right? So we're going to highlight the functional group and we're going to place R on it. So we need to recognize that, we have some carbon skeleton, and coming off of this carbon skeleton is a functional group that we're highlighting to really understand how to name it and the chemistry of it. So for example, if I have RH, that simply means that the hydrogen I'm kind of highlighting as a functional group. And so in this case, that is what an alkane is. Remember, an alkane is simply a hydrocarbon. We call it a hydrocarbon because it contains only carbon and hydrogen bonds. So the hydrogen is the functional group, right? Now there are different types of hydrocarbons. Alkanes are called saturated hydrocarbons, meaning that all of the carbons have as many hydrogens as they can possibly have on them. But we have different types of hydrocarbons as well. So for example, if I have in a carbon skeleton, so now I have all these R's, right? Meaning that they could be any carbon skeleton that I could possibly imagine. But in a structure, if I have a double bond, then the alkane becomes an alkene. And likewise, I can have a triple bond as well. So a structure that looks like this, where I have a carbon-carbon triple bond, and each carbon has an R group coming off of it, that's called an alkyne. So these are functional groups. Alkanes, alkenes, alkynes are functional groups. We have other types of functional groups that are not hydrocarbons as well. For example, when I have NH2 or NHR or NR2, so mainly a nitrogen coming off of an R group, this is called an amine, right? When I have an OH coming off of a carbon skeleton, it's an alcohol. When I have an SH coming off of a carbon skeleton, it's called a thiol. So again, recognizing the names of these functional groups is very important. Now, we have a wide variety of compounds where that contain a carbon-oxygen double bond. So and that's called a carbonyl. So if the carbonyl has two carbon skeletons coming off of it, it is called a ketone. Now, if the carbonyl has a hydrogen coming off of it and a carbon skeleton, it's called an aldehyde. So ketones and aldehydes are similar to one another. They have, and we're going to see they have similar reactivities, but they are separate functional groups, right? A ketone has two R groups, an aldehyde has one R group, and a hydrogen coming off of it. Next we have cyanide connected to a carbon skeleton. And when cyanide is connected to a carbon skeleton, this is called a nitrile. Here's another carbonyl compound with a chlorine coming off and an R group. This is called an acid chloride. Another structure that has a carbonyl with an oxygen attached to the carbonyl and then some carbon skeleton is called an ester. And then we can have a carbonyl with an NH2 connected to it, which is called an amide. These, so acid chlorides, esters, and amides are all we call derivatives of this structure right here, where there's an OH coming off of the carbonyl. So notice I have an OH coming off of a carbon skeleton that's called an alcohol, but if I have an OH coming off that's connected to a carbonyl specifically with a carbon skeleton attached to it, it is called a carboxylic acid. And acid chlorides and esters and amides are derivatives of carboxylic acids. So this is a brief preview of some of the functional groups. I'm not showing you all of them, but you can go back in your textbook on that front cover and you can look at all the various types of functional groups. So what I want to focus on in this chapter, as I said before, is alkanes. We're going to start off talking about alkanes. And I've mentioned before, but alkanes contain only carbon and hydrogen. And the cool feature about alkanes is their molecular formula. Very easy to determine because it's simply CnH2n plus 2. So if there are two carbons, then the formula is C2H6, right? 2n plus 2, so 2 times 2 is 4 plus 2 is 6. So C2H6, and you can readily determine the molecular formula of any alkane. Now be careful because there's also cycloalkanes, and cycloalkanes have different formulas. Now, as the name implies, cycloalkane is cyclic in nature, so it has a ring to it. And when you have a ring, you actually lose two hydrogens, and therefore the formula of a cycloalkane is CnH2n. So again, you can determine the formula of a cycloalkane very readily. Now this is a little bit tricky because what if you have a structure that has two rings? Well, again, for every ring you have to subtract two hydrogens. So if there's a two-ring system, it becomes CnH2n minus 2. If there's a three-ring system, it's CnH2n minus 4, and so on and so forth. Now, another aspect of organic chemistry is drawing organic structures. And there are a few ways of drawing compounds. And I want to highlight those ways, and we're going to certainly expand on the drawing of organic molecules throughout the semester. But in general, there's three main types of structures that we're going to be looking at. The first one, obviously, is the Lewis structure, which we've already looked at, right? So Lewis structure shows all bonds and all atoms, right? Now, a condensed formula takes that Lewis structure And what it does is it groups similar atoms together, right? So if there's, let's say, 3 hydrogens on a carbon, it's going to group it together as a CH3. The last structure that we're going to look at, and the most important structure, is called the bond line formula. Now, a bond line formula is a very abbreviated structure which shows only carbon-carbon bonds, right? So let's take a look at a few examples to kind of get us started. The first example, methane. Methane is the simplest alkane possible. It only has 1 carbon. We know what the empirical formula of methane is from general chemistry, CH4. We also know the Lewis structure has a carbon connected to all 4 of those hydrogens. So when we think about drawing a condensed formula, the condensed formula is simply, in this case, identical to the empirical formula because we only have 1 carbon, and so it is CH4. Now, for a bond line formula, remember bond line formula only shows carbon-carbon bonds. Methane has no carbon-carbon bonds, and therefore there is no bond line formula for methane. So let's look at something that has carbon-carbon bonds. We're going to take a look at propane. Propane has 3 carbons. It's C3H8. C3H8 is the empirical formula. And the Lewis structure for propane shows the carbons connected to one another and then hydrogens all around the carbons to give an octet of electrons to each carbon atom, right? Now, drawing all of those carbon-hydrogen bonds becomes kind of monotonous, and therefore we abbreviate it. In a condensed formula, we're going to take the 3 hydrogens on 1 carbon, we're going to simply combine them and say CH3. In the middle carbon, there are 2 hydrogens, so we're going to combine and say CH2. And at the end, there's also 3 hydrogens, so we're going to say denote that as a CH3, and it looks like this: CH3, CH2, CH3, right? So we've condensed the Lewis structure a little bit, but it still takes a while, and if we get into very large structures, even condensed formulas become a little bit of a nuisance. And therefore, the bond line formula, what is it going to look like? Well, the bond line only shows carbon-carbon bonds, and it doesn't even draw in the carbon symbol. So the bond line formula simply looks like this. It's 2 bonds, right? It's denoting the 2 carbon-carbon bonds that we have in that structure of propane. And so you need to be able to recognize in a bond line formula that the carbons on the end are CH3 groups. There are 3 hydrogens on each of those carbons. The carbon in the middle has 2 hydrogens on it. It's not represented, but it's implied that it's there. Let's take a look at another structure of a cycloalkane, and we'll take a look at cyclobutane. So butane, we'll learn, is 4 carbons, and cyclobutane is simply 4 carbons that are in a ring. And the Lewis structure looks like this. So there are the 4 carbons in the ring, and there are hydrogens attached to it. Again, the formula for cyclobutane is C4H8. And again, it becomes a little bit of a hassle to draw all of those bonds. So we can condense it a little bit, and you see that all of the carbons have 2 hydrogens on them, so we can simply draw it like this, and this is called the condensed formula. Now notice I've drawn the bonds in a condensed formula, and sometimes you'll see it written this way, and sometimes you'll see it with no bonds. But when you talk about rings, really you have to show the bonds associated with them. In a straight alkane chain like propane, oftentimes you can simply eliminate the bond lines in them. All right, so now the bond line formula of cyclobutane is pretty simple. All we're going to draw are the 4 bonds of the carbons, and those 4 bonds are connected to one another, and it simply looks like a square. This is the bond line formula of cyclobutane. Again, it's implied that the hydrogens are coming off of each of the carbons. The bond line formula is the one that organic chemists use the most. It's the easiest, it's the most practical in the sense of drawing structures in a timely fashion. And so, what does that mean? That means you have to get used to drawing them.